Hi, this is Mrs. Lemke, and I'm going to go through the Unit 6 review with you. It is a rather long review, so understand that that is the case. Certainly your assessment that you're about to take at home is not going to be quite as long as the review, but we wanted to make a very comprehensive review so that you had plenty of practice. The first question says, what has to be true of an equation to make it an exponential function? So an exponential function is one where you have a variable that is up in this position, up in the exponent position, and then this part here is something that is numerical. So something that would be like a number, a regular number, and then your independent variable is up here. And so in order to be a function, we would have to have x and y involved. So our y, or independent, or dependent variable, I should say, or our f of x would be over here, and then I'd have something that was a number, and then up here with the x, I might have other numbers as well, but I have to have that x in that position. So here is a complete statement of what I just said. You could also have something that is a number like this 2 in the front of my first example, or this 1,000 that's being multiplied. Remember that E, in spite of being a letter of our alphabet, is actually a numerical value, approximately 2.718. And so that is still satisfying the condition that the base would be a number, and your independent variable, the ones that I put the red arrow by, are our independent variable that's in the exponent position. Question 2 gives us a couple scenarios to look at. It says that you babysit over the summer. You're going to deposit some money, and you have the interest rate given there. You want to find the balance after 2 years if the interest is compounded monthly. So the compounded monthly is the one is telling me that I need to use this formula for compound interest. And if you kind of go through the statements or the question itself, the value that's called the principal, which is the amount that you put into an account or an investment, that's going to be $2,210. The interest rate is given as 3.25%. When I drop this percent sign to make this a decimal to fit into my formula, that's going to be 0.0325. for my R value. N is the number of times that the interest is compounded per year. And so since this says monthly, N is 2. And then it mentioned 2 years. So T is going to be 2. So that's going to be my general setup. I'm going to put those values into my formula and carefully work on my calculator. Now, if you try to plug all of this into your calculator at once, there are some tricky places where you do need to make sure that you have your parentheses right so that the calculator is doing order of operations in the way that you intend it to, right? It only is going to solve the problem that you type in. So I would recommend doing R divided by N. So in this case, that would be 0.0325 divided by 12 and hitting enter, adding the 1, hitting enter. And then N times T is not too hard to do, right? So that's an exponent of 24. And then take that answer and multiply by 2210. All right. If you want to type it in all at once, just make sure that you have parentheses in this location. And just to make sure that you're all good, I'd even put parentheses around this. And I would do that 24 myself because that's not too hard. 2 times 12, we can handle that. Part B said to figure out the difference in the money if you had continuously compounded interest, but everything else was the same. So if you see the word continuously, that means that you need to use the other compound interest formula, the one that spells out the word PERT on the right side. And so E is that number that I mentioned in problem 1, that 2.718, the base of natural log. And so you would substitute in your numbers. Still the same interest rate, still the same amount of time. Okay, make sure that your calculator understands that all of this is part of your exponent. And on the next slide, I have this written in nice handwriting. When I take my time, my handwriting's better. So here are the 2 numerical answers that you should get, and they only differ by 21 cents. So not a ton more. Generally speaking, you will get the most money from a compounded continuously situation, but because this is only for 2 years and kind of a low interest rate, it's not a huge difference in money. Okay, in question 3, we shift our gears into some graphing. And so in this problem, we are looking at the equation y equals 2 to the negative x. And I know I can think of that as 2 to the negative 1 to the x, right? Because a power to a power is where I would multiply. So negative 1 times x is the opposite of x. And then if I think about the 2 to the negative 1 part, another way to think of that is 1/2 to the x. So this given equation is the same as what I just wrote in red. And since the base is between 0 and 1, I know this is going to be exponential decay. So the shape of my graph overall is going to go like this. It's a downhill from left to right kind of graph. And it said that I needed to find at least 4 specific points. So I want to find some ordered pairs that I can plot somewhat easily. And since this side is higher, I think I'm going to use several that are on the negative part of the x-axis, because I think those will be easier to actually plot. At this point, you could use your calculator, but you can also use properties of exponents that you know, right? Because 1/2 to the negative 2, a negative is going to switch that inside part, the base, to be 2 over 1 raised to the positive 2, which is 4 over 1, or 4. And so I could continue doing that, right? Just use your calculator if you need to, and if you don't, then that is awesome, good for you. And then you're just going to plot the ordered pairs that you have. And hopefully it lives up to the expectation that you already have, right? This is going to be an exponential decay curve. Another point that you might have found that's reasonably easy to plot is at -3, the function goes through 8, so -3, 8. And here is my neat graph. Notice that I also included on my graph the horizontal asymptote, right? So exponential growth and decay have horizontal asymptotes. It's like where the curve comes down and kind of hugs that horizontal line as it gets closer and closer to it. So that would be a good thing to include on a graph, right? Or you might be asked a question like, where is the horizontal asymptote on this graph? That is a possibility. Okay, let's take a look at question 3, part B. So this is still also a graphing question, but in this problem, there isn't a negative on the x, so this is going to be an exponential growth decay, problem, not an exponential decay problem. It's going to look like this, and there's going to be an asymptote along here. And so I could find some ordered pairs by just plugging in values for x and finding the y that goes with them. So on this screen, I have already done that. And again, tried to show you where that horizontal asymptote is. Okay, I'm going to use this as a breaking point. Try to keep these videos short so it's easier for you to find the problem that you want. We will pick up on the next one with problem number 4.